You can learn to drive a car by getting the keys, having someone show you how the steering wheel, the gas, and the brakes work. Try it out in a quiet parking lot and then ease yourself onto the open road. And before long, you're able to get yourself to the grocery store and to a friend's house, and you can get done the basics. Now, contrast that with becoming a race car driver. In that case, you want to be able to get as much performance as possible out of your car. And to do that, you need to know how it works down to the nuts and bolts. That's the process of looking under the hood or opening the black box. If you want to get the most out of your tools, then how things work really matters. So to show you what I mean by this, for most of us, beginning machine learning or software engineers, this is what a support vector machine looks like. Here is the black box. You import scikit-learn, queue up a simple example and run it, and you're done. Here are the keys, here's the steering wheel, go. But to get the most out of it, you have to go deeper. My goal in this talk is to walk you through the process of going deeper, but more importantly, to show how any of us can go deep on any subject that we want to master. So as I tackled support vector machines, which were fairly new to me when I started this presentation, the first step I took was to read the scikit-learn documentation. This is what I came across. It's not particularly helpful to me being new to support vector machines. It's a nice, concise summary of the basic principles of how they work, but it doesn't explain it to someone who doesn't already know them well. One thing that the scikit-learn documents did provide was this great diagram showing here 2 different colors of points being separated by a line. That line looks kind of like a road where those 2 lanes are as wide as they can possibly get before they start touching data points. This was helpful. My next step was to go find a nice tutorial and read it. I found one that was highly recommended and started reading through it, and I saw definitions and tables and equations and graphs and diagrams and plots, and very soon got very overwhelmed, and there were theorems, for God's sake. And I felt strongly that it was probably important stuff, but it was not very accessible to someone who is new to the topic. So I took a step back, I set that aside, and I went to YouTube. And I pulled up some of the most popular videos on support vector machines, and in the course of doing this, saw multiple explanations of what they are, what they're used for, how to visualize them, how the math underneath them works. And the principles finally started to click. They began becoming clear in my brain. Following this, I went and found some more blog posts, again from a variety of posters, each with their own way of visualizing how they work, of explaining the principles behind it, and now the equations and the math and the definitions started to make a little sense. Enough so that I, in the next step, started to try to explain it to myself. And the way I do this is by drawing pictures. And so I started illustrating some of these concepts in a way that would make sense to me in my brain. Now that the ideas underneath support vector machines, at this stage, they're crystals, they're nuggets, but they're a scaffold, but they're not fleshed out. So to do this, I find it very helpful to choose a toy example. This is a bit of an art, it's trial and error, but finding an example that's simple enough that you understand it completely and you know exactly how it should work, but it's just complicated enough to illustrate the principle. So for this one, I settled on fruit. So imagine that we have fruit. It can either be small or large or yellow or purple. Now, any small fruit is a plum. If it's yellow, it's not yet ripe, but if it's purple, it's ripe and good to eat. Any large fruit is a peach. If it's yellow, it's great to eat, but if it's purple, it's rotten. You don't want to eat it. So in this example, we have in the world of peaches, there's a size axis and a color axis, and you can see the good things to eat are at the upper left and the lower right. Now, in this example, once you have this example, if you can get it to where you can explain it to, roughly like a 12-year-old, a 6th grader, which means that you use words and ideas that are common, no jargon, or if you do use a jargon term, you explain it thoroughly. So here's my attempt to do that for support vector machines. So imagine you have peaches, and they can be any color between yellow and purple, and you would like to figure out which ones are good to eat. You'd like to know, in fact, if you get a new peach based on its color, whether you should eat it or not. So what you do is you get a bunch of peaches and you grab one and you try it. You get one that happens to be yellow, you taste it, it's good. So you make a green circle and put it at the point that represents its color. You grab another one that's pretty purple and you taste it and it's nasty, it's rotten. So you put a black X at the point that represents its color. And you do this again for a few more peaches, some yellow ones, some purple ones, some ones in between. And before long, you have a data set that looks like this. The green circles all show good peaches, the black X's show bad peaches. Now that you have all this data, you would like to make a prediction. Based on a peach's color, do you expect it to be good to eat? Support vector machines allow you to do this. And what they do when you have two groups of data is they come and they put what looks like a road in between them. There's a dotted center line and then two lanes, and it tries to make that road as wide as it can possibly get until the outside of those two lanes bump up against your two data sets. The center line is the divider between the two groups. Anything to the left of that will be assumed to be good to eat. Anything to the right of that will be assumed to be bad to eat. And the lanes on either side are called margins, for lack of a better term. Now, imagine though that in this set of peaches, this can be trickier. What if you have some that don't really fall with the group? You get some yellow peaches that just don't taste right, or you get a purple peach that for some reason tastes amazing. Now the data set, there's nowhere you can draw a line that separates the green circles from the black X's. But what you can do is still create a dividing line with its margins, but any data point that is on the wrong side of its margin gets a penalty based on how far it is over. And so you can move the position of this dividing line and the width of its margins to take that penalty and add that penalty in and still make that as small as you possibly can. So you can still use support vector machines in cases where your data isn't completely separate. The fancy term for that is linearly separable. Just means you can't separate it with a line. So it can handle non-linearly separable data. Now let's look at a different case. Instead of just peaches, we have peaches and plums. The good ones, we either want to eat yellow peaches or purple plums. A yellow plum isn't ripe and a purple peach is rotten. So we can do the same thing in this world. We try a bunch of fruit of different sizes and different colors. We find that the yellow peaches are delicious. We find that the purple plums are delicious, but the yellow plums are terrible and the black peaches, the purple peaches are terrible. So we end up with a data set that looks like this. The challenge now is that if we try to draw a line to separate these out, it's not just that a few data points are going to be a little bit off. There's a whole chunk of our data that we're missing. We're not capturing it well. So this data is obviously not linearly separable. To help us visualize this, I went and took it into Python and made a different visualization of it. But it's the same thing, green circles and black X's. We'd like to try to separate them. And in this case, we can't with a line. Now, support vector machines have an answer to this. What you do is you imagine that all of these data points are not on a flat plane, but they're on a sheet of rubber. And you can pick that sheet of rubber up and you can stretch it and bend it and warp it however you want. And you can probably visualize here that if you take that and bend it just right and slice it you can separate out the good to eat fruit from the bad to eat fruit. And this is exactly how you would do it. If you can now, with a single straight slice, you can separate these things out nicely. This trick of bending your sheet of paper, of warping it, is called the kernel trick. And it refers to how it's calculated. But in practice, all you need to know is you can take this space that your data is in, this paper that it's on, and twist it and bend it however you want. You can take and hold down the middle and pull up all four edges. Or you can pull up all four edges and pull up the middle and leave a little ring low around the middle, or low around the center. Or you can take it and pull it up and pull it down and make it like an egg crate so that you can capture really irregularly spaced data, and with a single slice, you can separate it all out from each other. So the kernel trick is really powerful. And in fact, there is no limit to what you can do with this space to bend it. To illustrate another way that it's powerful, let's consider a slightly different problem. Now we have fruit. We don't care about the size, but we have 5 different colors. Green peaches are unripe. They're not yet ripe. Yellow peaches are ripe, so they're good. Orange fruit is an unripe plum, and a purple is a ripe plum. And then a black fruit is rotten. So the good ones to eat are the yellow peaches and the purple plums. Any other color is bad to eat. Now you can see that all of this data is just on one line, but there's no nice way to slice it to separate the green circles from the black X's. Now we can use the kernel trick. We can take that line essentially and bend it however we want. One way to do that is to just make a single bend in it, like a smiley face. And you can see that, great, we bent it, but still those circles and X's are not laid out so that with a single cut, we can separate them from each other. Now, the cool part about the support vector machine kernel trick is that you can come back and bend your space again in a different direction. So this represents a 2-dimensional kernel. And now it's not too hard to see that with the right slice, you can come in there with the plane and separate out those green circles from those black X's. Now, if you look carefully, you'll notice that this slice is actually not exactly the one you'd want. It kind of misses, but you can imagine where it would go to separate those out. So here we did 2 different warpings. We took our line and we bent it one direction, and then we bent it another direction. Because of the math, it's a little bit mind-blowing, but you can actually take whatever space your data is in, and you can bend it in an infinite number of directions to make it so that you can slice it and separate out your 2 groups of data. So that is pretty powerful stuff. This is what support vector machines do. They take and find the best slice that separates out 2 groups of data, and if your data is hard to separate, you can warp and twist your space until you find a way to separate it. Okay, so that's the explanation. Now comes the most important part. In addition to understanding the strengths of a method, you have to understand its weaknesses if you're going to use it well and push it to its limits. So, with support vector machines, issues include if you have data with lots of error. So if you notice, any time that we're finding a slice between 2 groups of data, the location of that slice depends almost entirely on the very nearest data points. The other ones, it doesn't matter if they're close to the margin or miles away from the margin. It's those nearest data points that determine exactly where that margin is going to be. And if each of those has a lot of error associated with it, then that error gets a really loud vote, more so than most of your data. So that is an issue. Another way that it can break is if you choose the wrong kernel. If you look back at the original data set where we were bending our paper like a sheet of rubber, if we bent it the wrong way, we would not be able to separate out our data sets. We had to bend it just the right way. That's choosing the right kernel. And the act of choosing the right kernel is an art, and it's done by trial and error and, after a while, by experience. And then finally, large data sets can break support vector machines. Calculating the kernel, some kernels especially, can be very expensive, take a lot of computing power. And so if you're not dealing with just hundreds of data points, but billions, then the amount of time to calculate those is prohibitive. So with large data sets, you have to stick with linearly separable problems. So you have to go back and hand engineer features that help your data get separated out. Help it so you can separate it with a straight line, single cut. So each of these requires a human in the loop to determine when it's a problem and to work around it. This is important to know. This means that support vector machines are powerful, but to get the most out of them, you need someone who has used them quite a bit and understands them well. This doesn't mean that they can't be used, but this is important to know when you're deciding what method to use on your problem. Now, taking a step back, that was a quick walk through support vector machines. Hopefully you understand it now a little bit better than you did before if you were new to it. And now going into another project, you know what you need to do to make good use of it. A comment on the process. We went through this together. There was no formal education, no coursework, no textbook, no professor, no permission granted, no special libraries, nothing purchased. This is all information that's out there. This is something that you can do with any tool you want. You can take and open the box and see what's inside. You can lift up the hood and you can see what the pieces are and how they work together. It's not an easy process, and sometimes it's quite painful, but it is something that you have at your disposal. And it's something that, in the cases of my key tools, I have found it very worth my while. So I encourage you, when you have something that you think you might need to use heavily, take some time, open the box, figure out how it works so you go from a grocery getter to a really high-performing race car. Thank you.